Okay, let me do a quick sidebar here because there is a question some of you may have at this point and I want to deal with it. But Simon, you say, you showed us this machine code gobbledygook and you said that is what the computer understands. But I've always heard that computers understand ones and zeros and that machine code did not look like ones and zeros. What's the deal? Okay, computer chips, these CPUs, are at their most microscopic, fascinating, magical, mind-boggling, yet also slightly boring level, made from billions with a B of almost unimaginably tiny electrical switches, each one either on or off. If I could take this CPU and a scanning electron microscope, and there are videos on YouTube where people actually do this, and zoom in and zoom in and zoom in, we would eventually get to millions or billions of these tiny electrical switches or transistors on this chip, each one closed or open, on or off. To be clear, to be a successful programmer, you don't have to know anything about CPUs, integrated circuits, transistors, or capacitors, or bistable flip-flops. That's hardware, we're software, different skill set. Like a surgeon needs to know how to use a scalpel or an EKG machine, but they don't need to know how to make one. What is good is to know enough about a CPU that we don't just think it's a bunch of magical leprechauns making our programs work. And okay, I'm simplifying. There is way more to a modern CPU than just lots of transistors, but still, it's different combinations of these switches, different groupings and arrangements of them that are used by the CPU together with other parts of our computer like our memory modules to represent number values and represent text and hold graphics and audio and all the programs that you're running at any moment and exactly what they're all doing right now. And yes, that can seem puzzling. It isn't immediately obvious how we can take a bunch of tiny on-off switches and say, this bunch is now a Bach concerto, and that bunch of switches is a picture of an alien spaceship. Well, okay, I can't show billions of switches, so let's begin with, for example, 1. I'll use this symbol for a toggle switch. It's either on or off. And the important thing here is not whether this is connected to something or causes something to happen elsewhere. No, it's the switch itself, just by itself. Because I can decide what I want this to mean. And what it represents is up to me. And it can be different in my program than in yours, as long as what it represents only has 2 options. In a computer program, I might decide that this means a user is either logged in or not logged in. I could use another one to say we are currently recording or we are currently not recording. But what I can't use one of these for is anything more complex. I can't use one switch to represent a bank balance or the result of a horse race or a PDF invoice. But I can add more switches. I can group them together because we have a ridiculous amount of them available. And if I have a group of 2 switches, I go from 2 possible values to 4 possible values. Both of the switches off, one off and one on, the other way around, and both of them on. Okay, fine, this is still simple, but whenever I add a switch, I'm not just adding 2 additional options, not just another on-off. I'm actually doubling the amount of values we can hold. Okay, when we go from just 1 to 2 switches, it's unimpressive. We need to take this further. So with 2 switches, I have those 4 arrangements we just saw, still very basic. If I add 1 more switch, then I have these same 4 arrangements I had a second ago with this new 3rd switch off, and also those same 4 arrangements from a second ago with this new 3rd switch on. So I've gone from 4 to 8 possible arrangements of 3 switches. Every time I add 1 switch, I double the possible values again. All the arrangements from before with the new switch off, as well as all the arrangements from before with the new switch on. So it rapidly increases, always doubling. With 3 switches, it's 8 possible arrangements. With 4 switches, it's 16. 5 switches is 32, then it's 64, then it's 128. And when we have just 8 switches, there are already 256 possible arrangements of these, from all of them off, all of them on, and everything in between. I've been using these toggle switch icons, but these are getting to the end of their usefulness. I can't really fit any more. But I still need a way to describe these arrangements. I suppose it's true I could use words to represent them, but that's kind of clunky. Or what I can do is use a 0 for an off and a 1 for an on. A very compact, concise way to do this. And it is 0s and 1s we use in computing. This is binary code, and we use it as a way to represent that most basic, most fundamental state of just part of a computer. There aren't really 0s and 1s bouncing around inside your computer. They are just ways we can represent or visualize those tiny elements being on or off. Now let me correct myself. I've been calling them a switch, but in computing, we don't call each of these elements a switch. We call it a bit, for binary digit, the tiniest element of information that is either 0 or 1. So in all of these examples here, I have 8 bits, 256 possible arrangements, from all zeros at the top to all ones and everything in between. So I could use a group of 8 bits and decide it represents some modest number I need to keep track of, perhaps the amount of enemies on screen. As long as I know that number never needs to be more than 256, 8 bits is all I need to keep track of it. If I need to store bigger values, I add more bits. And because computers really are built on this binary idea, it is easier to deal in multiples of 2. If I go from 8 bits to 16, we go from 256 to about 65,000 possible values. Double it again to 32 bits, we're already at 4.3 billion possible values. With 64 bits, it's, well, I don't know how to say this, but it's a lot. Now, you may have even heard these phrases like, things are 32-bit architecture or 64-bit architecture, and that refers to the amount of bits that the CPU is most happy in dealing with and moving around. The larger, the better, typically. No modern CPU just wants to deal with one measly bit at a time. It's just not that useful. But here's the thing, 64 bits can represent this huge number, but I don't have to use these just to represent a number, because I could also take this same 64 bits but decide I will use this particular collection of information to represent an 8 by 8 pixel area of the computer screen and use the zeros and ones to turn 64 specific pixels on or off. And that's how we can take a few on-off switches and use it to represent a picture of an alien spaceship. So, back to that machine code. Why isn't this ones and zeros? Well, it kind of is. Let me explain that with bananas. If I'm a grocer and at the start of each day I count the bananas I have for sale, whatever that amount is, I could write it down with words, 27. Or I could use decimal digits, a 2 and a 7. Or Roman numerals, XXVII. Or I could use marks on a chalkboard. Or I could use my hands. Or I could use little pictures of bananas. Whichever one I use, they all mean the same thing. None of these values are approximate. They're all exactly 27. They are different methods to convey the same information. We will use whatever method is most useful at the time, usually which one is going to be the most concise and compact way to do it. And that's what's happening here. Machine code can be shown in binary, but it's more common to use a format called hexadecimal, or hex. We can view more information in a smaller area using hex than using binary. If I have any of these groups of 8 bits and I need to describe those arrangements, with binary I need 8 ones and zeros. But using hex, I just need 2 digits, because each digit of hex can have 16 different values, from 0 through 9, but also A through F, instead of just the 2 different values, 0 and 1, that we get with each binary digit. So this in binary becomes this in hex. So when we see machine code, it is the specific details of exactly which bits are 0 and which bits are 1. It's just using a more concise way to display it. Now, right now, we do not need to get into the details of writing binary or hex or translating from one to the other. It is not necessary when you're beginning. But do know that in the rare occasion where a programmer needs to look at information so specific, it is usually more convenient to view it in hex than view it in binary. And that is absolutely as deep as we need to get into this right now. End sidebar, time for the next module.